In quantum mechanics, canonical quantization is obtained by imposing that the commutator between a dynamical variable and its canonical conjugate do not commute, and in particular it's equal to I. If we are in the Heisenberg picture, where the time evolution is on the operator, not on the state, then this commutator is defined at equal time, so Q and P are both at the same time. If we generalize that to field, now the dynamical variable is the amplitude of the field at a given position in space. We get canonical quantization by imposing a similar commutator between phi and its canonical momentum pi. Again, this commutator is defined at equal times. But now in quantum field theory, we have as many dynamical variables as we have position of space. So the only when the position is the same, do we have pi being the canonical momentum conjugate of phi. And that's why we have a delta function between x and x dash on the right-hand side. So let's see how it works for the case of a Hermitian free field, which in classical field theory just means that we have a real field. So phi is equal to phi star. Now that we have operator, this means phi operator is equal to the Hermitian conjugate of phi. So we are looking at a free field, therefore its Lagrangian is given by the Klein-Gordon Lagrangian. And in order to work out the canonical conjugate, we need to expand the derivative, the covariant derivative, in terms of its time and spatial components. The canonical momentum density is then given by definition, it is given by the derivative of the Lagrangian with respect to the time derivative of the field. So in the case of the Klein-Gordon Lagrangian, that gives us the time derivative of the field itself. But for another Lagrangian, we could get a different expression for the canonical momentum. In canonical quantization, we start from the classical equation of motion, and then we quantize them by changing the dynamical variable into an operator. The classical equation of motion are obtained from the Euler-Lagrange equation, which gives the Klein-Gordon equation. Now we canonical quantize by changing phi into an operator. We already worked out a solution of the Klein-Gordon equation. This is a sum of positive frequency and negative frequency solutions. Now, because we have a Hermitian field and phi dagger is equal to phi, we need to have a dagger here. We can't just take an arbitrary amplitude b, for instance. For this to be a solution of the Klein-Gordon equation, we need to have an expression for omega k. Indeed, if we plug this solution into the Klein-Gordon equation, we see that we have terms like and similarly for the negative frequency term. So far we have just promoted the field as an operator. We still need to impose the commutation relationship at equal time. And when we impose this relationship, what we get is the following commutators for A and A dagger. We will show it the other way. We will assume these commutators for A and A dagger, and we will show that they lead to this commutator for phi and pi. And for that, we need an explicit expression for pi. So we see that the commutator will decompose into commutators of A of k with A of k dash, but we already know that this one is 0. It will also have a commutator of A dagger of k with A dagger of k dash, which is also 0. Therefore, the only terms which are going to survive are those which involve a commutator of A of k with A dagger of k dash and A dagger of k with A of k dash. The commutator of A with A dagger will give us a plus delta function, and the other term will be a commutator of A dagger with A, which is minus the commutator of A and A dagger, and therefore that will give us a minus delta function. So both are proportional to delta, which we can factorize. Because k has to be equal to k dash, we see that the exponential minus I omega kt and plus I omega k dash t cancel in both terms. The square root of omega k dash becomes just omega k, while the omega k dash here becomes also omega k and cancel with this one. So this is just a cosine function, and because the integral runs from minus infinity to plus infinity, we see that this is the same thing if we take a plus in the exponential or a minus. We recognize an expression for the delta function. So we recover the commutation relationship at equal time, meaning that we indeed have these commutation relationship for the A and A dagger operators. If we stare at this relationship long enough, we recognize something familiar for the harmonic oscillator. In this case, these are the lowering and the raising operators. So from this analogy, we expect the Klein-Gordon Hamiltonian to look like a harmonic oscillator.